Wasabi, you guys. Welcome to Integration Be Training for Advanced. This is part 20.2. So in this section, we're going to be learning the full Glasser's master theorem. Okay, so what is the full version of the Glasser's master theorem? It states that whenever you have a function that is in terms of x minus whatever the sum from n equal to 1 to infinity, and we're going to write it like this. You have a positive number on top, and then x minus any real number. So what this is a of n and c of n. These are like real numbers. Okay, they're not functions. They're just any number, any real number where it has to be positive on top and x minus whatever number this is, right? It has to be real, no complex. Okay, no matter, and it could be the sum whatever. So it could be like randomly, literally, let's say it could be like 1 over x minus 1, or it could be minus 1 over x minus 2, or x minus pi for no reason, x minus e, x root 2. Then it could be whatever, how many times, not infinitely. Oh, actually, yeah, infinitely. Yeah, infinitely. Yeah, it can go on forever, honestly. Yeah, a function in terms of this, which obviously we're not gonna, because that's just insanity. But in general, it could be however many times. This could be 4. It doesn't have to be in order. Whatever the numbers are. The top can be even, as long as the top is positive. There's no pluses. They're all minuses, right? This could be pi. This could be tau. 4 factorial, I don't care. Whatever positive number this is, as long as it's subtraction, right? This will always be f of x. Or, yeah, in Glasser's master theorem, it's still the same thing as f of x dx, okay? I swear to God, I'm not going crazy. But this is literally Glasser's master theorem. I'm not joking. Whatever this is, okay, if it's in whatever, I don't care, right? It could be 42 terms, whatever. It's still going to be in terms of f of x. It's still going to equal to f of x from negative infinity to infinity. I know. The proof is wild. It is complicated. I can barely even understand the proof because it's so terse. But this is true. This is real. This is legit. Wolfram Alpha would not probably understand it, but it'll get the correct numerical answer. But yeah, this is real. Okay, so this is what we're going to be using, but we're not going to use something ugly like this. No, like you'll never come across something like that in Integration B. Okay, just kind of like just a little smaller versions of this. You'll see as we get to the examples. Okay? Alright, let's go ahead and start these examples. I don't even have to do anything. Like in this section, we're gonna blaze through all these integrals. Because it's now that we know the full Glasser's master theorem, it's super easy. Okay? So go ahead and solve this integral like in 3 seconds. What is this? Pi. Yeah. You already see it. This is equal to pi. Right? We know that this is equal by Glasser's master theorem, right? Because it follows we have some positive integers here because they're all subtracted. All of our denominators are linear, right? Would you look at that? This is equal by Glasser's master theorem. This is equal to dx, 1 plus x squared, right? So this whole thing is just x. Okay? I swear to God, I'm not crazy. I'm not crazy. Okay? I'm not the one who made this. Okay? Lawrence Glasser did. ML Glasser, I forgot what M stands for, but something like Lawrence Glasser? I could be wrong. But Glasser made this, okay? Not me. Okay, I'm not the crazy one here, but this is actually true. This does equal, and of course the answer is indeed pi. Okay, you don't believe me? Plug that into Wolfram Alpha. Even Wolfram Alpha says this is equal to pi. So this is true. So now, what does this integral equal? What is it? What is this integral equal to? Secant of x. If you say that this integral is equal to such hyperbolic secant of x, you are incorrect. This is wrong. You have mistaken your usage of Glasses' master theorem. You cannot use Glasses' master theorem, and let me tell you why. And this is because we have a 2x. Okay? You cannot do that. So what do? U substitution. So let u equal 2x, you get a half of hyperbolic secant of u minus 1 over u minus 1 du. And now you can go ahead and use Glasses' master theorem. This is a half of infinity to infinity sec of u du. Okay, so now after this is equal to a half. We turn this into hyperbolic form, right? This is like 2, that cancels out. E to the u plus e to the negative u du. We can go ahead and go like this. This is simply, if you let e to the u, this is what, 0 to infinity of du of u squared plus 1. So this is going to equal to like, what, inverse tangent, half, pretty much, yeah. Pi over 2. So our answer is pi over 2. Okay? Very simple. Okay. So be very careful with that. Okay, you cannot use Glasses' master theorem like this. You have to do a u substitution to make sure that this is like MONIC. Okay? Alright, solve this integral now. What is this? How do we solve this? Can we use Glasses' master theorem on this? Yes, we can. But why? Why can we use this? If this is not a linear function at the denominator, how are we able to still use Glasses' master theorem? That's because we can do partial fractions, right? If you perform partial fractions with this, we get x minus, and then here we do partial fractions, okay? If you do partial fractions, you get something like a half here for like x plus 1, and then minus a half here, I think. Yeah, x minus 1 here, right? Look, see, partial fractions, and we still get the form that we can use on Glasses' master theorem. So by Glasses' master theorem, this is, you know, the same old inverse tangent integral. This is pi. Okay, so just be aware, if you see something like this, partial fraction it and see if it, you know, see if it can be applied with Glasses' master theorem. And in this case, it can. Okay. Oh God. All right, don't panic. We stumble across an integral, something very serious now. We are on a serious level of integration. So what do we do? Well, I see a lot of squares. So, and negative infinity to infinity. So that's very suspicious. So we might be able to do Glasses' master theorem, but how? Well, first I want to know, what on earth is this ln? I want to know what this ln is. Right. We have x squared minus 3 plus 4 over x squared? Huh. Interesting. And then we just have x squared minus 2 squared. This is very interesting. This can actually be complete the square-ish. So what I mean by that is it can be ln of x minus 2 over x squared. Ah, so we can do that. And then this is going to be like plus 1. Oh, wow. That's very nice. Okay. And then here, this is, oh, now I'm starting to see the picture. If we let this be reciprocated, right, x squared minus 2 over x, that's equal to x minus 2 over x. Would you look at that? Can we use Glasses' master theorem? Yes, we can. Yes, we can. So now we have ln of x squared plus 1 over x squared dx. What do we do? Integration by parts, right? This is simply integration by parts. Ln of x squared plus 1. This is x squared plus 1 minus 2x. This is 1 over x squared. If we integrate, this is minus 1 over x, right? Oh, how perfect! That is beautiful. So now we have ln of x squared plus 1 over x. I'm sorry, this is negative. And then we have like plus 2 inverse tangent of x from negative infinity to infinity. Wow. Okay. That's crazy. So this side here is, let's see, if I plug in infinity, that's like, that's equal to 0. I think it is 0. Yeah, that's actually 0. So this side becomes 0, and so pi over 2, negative pi over 2. So it's going to be 2 pi. Yeah. So the answer that we have is 2 pi. Okay. This I just did L'Hopital, and for any infinity, it's just going to be 0. And here it's just, you know, pi over, it's pretty much pi times 2. So 2 pi. So this integral is equal to 2 pi. Okay. So again, it doesn't have to be x minus 1 over x. It could be x minus 2 over x, or 3 over x, or whichever. Okay? Okay, we are down to our last integral example here. So we have something very scary. We have 2x, but this one we have just regular x. But thankfully these two here, notice that there's 2 and 2 and 2. We can factor out the 2, and we get this at the bottom. So in other words, we pretty much have, this is not what it equals, but it looks like this. Right? It looks like this. Or if we call this alpha, so that we don't get it mixed up as like an actual integral. But what is 1 minus cosine of 2 alpha? This is equal to sine square alpha. Oh. I think we know. I think we get the gist of what's going on here, right? What we have is this is equal to sine square of x minus 1 minus 1 over x. And then we have x minus 1 minus 1 over x squared, right? I'm sorry, this should be 2. That should be 2. Okay? Don't forget that. Okay, and now, can we use Glasses' master theorem? Yes, you can. Yes, you can. You technically can. With that minus 1 still, yes, you can. So, that means that what we have here is 2 sine square x over x squared dx, which is equal, we know this is pi over 2, right? By Dirichlet integral times 2. This whole integral is equal to, oh, I'm sorry. No, it's not just pi over 2, because we have infinity to, from negative infinity to infinity. So this is technically 2 pi. So what we have here is our answer is 2 pi. Okay? And we're done. There you go. You just learned the full ability of Glasses' master theorem. Now, if you're still learning calculus in your class, don't show this to your calculus teacher, or they will call you a psychopath. Okay? Because they will not believe you that this theorem is true. So, if you're doing some homework, don't use Glasses' master theorem, or you will get docked points. unless your teacher's very chill. But it's like it's one of these like illegal. It's not an illegal integration technique, but it's one of those things where it's just like if you show this to math or calculus teachers, they're gonna think you're crazy. So, but yeah, this is a very powerful Glasses master theorem. It's this powerful. It's insane. Okay, but we're not done here because we do have a last section for Glasses master theorem that I want to show you. So stay tuned for that. Other than that, practice the integrals, and yeah, I hope that helps. Thank you so much for watching, and I'll see you guys in the next part.